Good morning to all. I am Prabavathy, Assistant Professor, PG and Research Department of Mathematics, A.D.M College for Women, Autonomous. In first slide, I already explained about the basic concepts of differential equations, order, degree, and principle of superposition, application of differential equations, etc. Today, in this module 2, I am going to discuss about higher order linear differential equations of homogeneous and non-homogeneous type. First, we will recall second order linear differential equations. The typical second order linear differential equation with constant coefficients is given by the relation AD square plus BD plus C into Y equal to capital X, where A, B, C are arbitrary constants. Capital X is a function of X. So the symbol capital Dy denotes the first derivative of Y with respect to X, that is capital Dy is equal to dy by dx. Similarly, the symbol d square y denotes the second derivative of y with respect to x, that is d square y is equal to d square y by dx square. Now, we will see the definition of higher order linear differential equations with constant coefficients. The nth order non-homogeneous linear differential equation with constant coefficients is given by the relation a0 d power n plus a1 d power n minus 1 plus a2 d power n minus 2 and so on plus an into y equal to f of x. Let us denote this as equation number 1. The nth order homogeneous linear differential equation with constant coefficients is given by the relation a0 d power n plus a1 d power n minus 1 plus a2 d power n minus 2 and so on plus an into y equal to 0. This equation is denoted by equation number 2. This is obtained by putting the RHS of equation 1, that is f of x equal to 0 in the differential equation 1. So the symbols in equation 1 and equation 2, that is a0, a1, a2 and so on an, are arbitrary constants, and f of x in the right hand side of differential equation 1 is a function depending on the variable x, and the symbols d power n y for any n denotes the nth derivative of y with respect to x, that is d power n y is equal to dny by dx power n. We already see that dy is first derivative, d square y is second derivative, d cube y is similarly third derivative, so d power n y is nth derivative. Now we will see the general solution of linear differential equations of any type, homogeneous or non-homogeneous. So this is of the form y of x is equal to cf plus pi. We denote this as equation number 3. Here cf is nothing but c1 y1 plus c2 y2 and so on cn yn. This is the general solution of the corresponding homogeneous equation 2, and it contains n arbitrary constants. This is denoted by equation number 4. And in first module we will see that what is principle of superposition. It says that if y1, y2, yn are n linearly independent solution, then the linear combination, that is c1 into y1 plus c2 into y2 and so on cn into yn, is again a solution of the equation 2. So we are using that. And also PA. PA means particular integral, that is particular solution of the equation number 1. So the solution of the non-homogeneous type is combination of CF and PA, and the solution of the homogeneous is only the CF. It is known as the general solution of the homogeneous higher order linear differential equations. To find the complementary function, we need some formulas. So now we will see how to find the formulas. So for that, we have to substitute, that is we have to replace the capital D by the symbol small m. Then the auxiliary equation of equation 2 is of the form a0 into m power n plus a1 into m power n minus 1 plus a2 into m power n minus 2 and so on plus an equal to 0. We will denote this as equation number 5, and this is not a differential equation. This is an algebraic equation of degree n. So we can use the fundamental theorem of algebra. It says that any polynomial of degree n has at most n roots, so that the equation in equation number 5 have at most n roots. So the n roots have different nature. So according to the nature of the roots, we can divide into 3 cases. So first case, if the obtained n roots, we will denote as m1, m2, m3 and so on mn. If all the n roots are distinct real roots, then the complementary function will be given by the formula y is equal to c1 into e power m1x plus c2 into e power m2x plus c3 into e power m3x and so on plus cn into e power mnx. Here e power m1, e power m2 are exponential functions. So next case, if the two roots are equal roots, if the two real roots are equal, then the complementary function will be y of x is equal to c1x plus c2 into e power m1x plus c3 into e power m3x plus c4 into e power m4x and so on. If two roots are complex roots and other roots are distinct or equal real roots, then the complementary function will be of the form y of x is equal to c1 plus c2 in c1 into e power alpha x into c1 cos x plus c2 sin beta x plus c3 into e power m3x and so on. Now we will explain this procedure by means of some solved problems. So problem number 1, that is, if we suppose we are given that solve d square plus 5d plus 6 into y equal to 0. We already seen that that's capital D denotes the derivative of y with respect to x. So y is the dependent variable depending on the independent variable x. So to solve this problem, first we have to substitute that capital D equal to small m. Then the auxiliary equation will be m square plus 5m plus 6 equal to 0. So we have to solve this algebraic equation. So we should be familiar with the solution of algebraic equation, how to find solution of second order cubic equations and biquadratic equation solutions. So here our equation is a quadratic equation. So by observing that equation, we can see that the number 6, that constant, can be written as a product of two numbers, that is 2 into 3. So 6 can be written as 2 3s are 6 and 5 can be written as 2 plus 3. So this equation can be factored into m plus 2 into m plus 3 equal to 0. From this equation, the solution, the values of m will be minus 2 and minus 3. We can see that these are real roots and they are unequal roots. So we have to go for the case 1. In this case, the complementary function is given by CF is equal to C1 into e power minus 2x plus C2 into e power minus 3x, where C1 and C2 are arbitrary constants. So next problem, capital D square plus AD plus 16 into y equal to 0. Similarly, as in for problem 1, here also we have to replace the capital D by the notation small m. So the auxiliary equation is m square plus 8m plus 16 equal to 0. So it is also a factor into m plus 4 into m plus 4 equal to 0. So the values of m are repeating twice, that is minus 4 minus 4. So they are real and equal roots. So the complementary function is CF is equal to C1x plus C2 into e power minus 4x, where C1 and C2 are arbitrary constants. So for case 3, the example problem is capital D square plus 2D plus 5 into y equal to 0. So the auxiliary equation is m square plus 2m plus 5 equal to 0. Here the 5 cannot be factored as a two numbers because it is a prime number. So we have to go for the formula, that is a famous formula, quadratic formula. So that is m is equal to minus b plus or minus root of b square minus 4ac divided by 2a. In the above equation, a is equal to 1, b is equal to 2, c is equal to 5. Hence, m is equal to minus 2 plus or minus root of 4 minus 20 divided by 2. By solving this equation, we can observe that m will be having the value minus 1 plus or minus 2i. Here alpha is 1, beta is 2. So similar way, we can solve the problem d square plus d plus 1 into y equal to 0. So again we are using the quadratic formula and we are getting the values as complex root, that is minus 1 plus or minus I into root 3 divided by 2. The roots are complex. So complementary function will be CF equal to e power minus 6 by 2 because alpha is 1 by 2, beta is root 3 by 2. So C1 into cos root 3 by 2 into x plus C2 into sin root 3 by 2 into x. Now we are going to for the higher order equation. So I already mentioned you that we are going to solve higher order differential equations. So first we are starting with order 3. So put d equal to m in the given equation. So auxiliary equation will be m cube minus 3m plus 2 equal to 0. So this kind of cubic equation cannot be solved as in the quadratic equation. So we have to use here the synthetic division and trilateral method. So we observe that the coefficients 1, minus 3 and 2. If we add these coefficients, the answer will be 0. So from this we can determine that m equal to 1 is the root of this equation. So by using that root, we can determine another roots by means of synthetic division. So by using the synthetic division, we can factor this equation as m minus 1 the whole square into m plus 2 equal to 0. So the values of m will be 1, 1, minus 2. So first two roots are real and equal, and the third root is also real, but it is different from first two roots. So the complementary function will be CF is equal to C1x plus C2 into e power x plus C3 into e power minus 2x, where C1, C2, C3 are arbitrary constants. So next problem, that is order 4, that is by quadratic equation. So put D equal to m. So the auxiliary equation will be m power 4 plus 8m square plus 16 equal to 0. So this equation can be factored into m square plus 4 into m square plus 4, which is equal to 0. So m square will be minus 4. It is repeating 2 times. So minus 4. If we solve that, we get m is equal to plus or minus 2i. So here complex roots always occur in conjugate pairs. So the complex of conjugate pairs occurring 2 times. So the 4 roots plus 2i repeating 2 times minus 2i repeating 2 times. So the roots are complex roots and equal. Hence the complementary function is given by the formula CF is equal to C1 cos 2x plus C3 into x into sin 2x and C2 cos 2x plus C4 into x into sin 2x. So this will be rewrite like this. So C1, C2, C3, C4 are arbitrary constants. And the next problem is cubic equation, that is d cube plus 2d square minus d into minus 2 into y equal to 0. Here if we substitute d equal to m, the auxiliary equation will be m cube plus 2m square minus m minus 2 equal to 0. So again, we have to observe the coefficient of the equations, that is m cube coefficient is 1, m square coefficient is 2, m coefficient is minus 1, constant is minus 2. If you add all these coefficients, the answer will be 0. So m equal to 1 is the root of this equation. By using that equation, we have to solve by using the synthetic division. We get the solution as m is equal to 1 minus 1 minus 2. This is according to the case 1, the roots are real and distinct. So complementary function is given by the formula CF is equal to C1 into e power minus x plus C2 into e power x plus C3 into e power minus 2x, where C1, C2 and C3 are arbitrary constants. So next problem also cubic equation. So d cube minus 3d square plus 3d minus 1 into y equal to 0. To find the solution, we have to replace d by m. So the auxiliary equation is given by the relation m cube minus 3m square plus 3m minus 1 equal to 0. This is a famous algebraic equation formula, that is a minus b the whole cube formula. According to the formula, this equation can be factored into m minus 1 the whole cube. That is m have 3 values, they are 3 equal roots 1, 1, 1. So in this case, the complementary function is given by the relation CF is equal to C1 plus C2x plus C3x square into e power x, where C1, C2, C3 are arbitrary constants. So now the last example, solve d power 4 minus 1 into y equal to 0. So to solve this problem, we have to substitute d equal to m. So auxiliary equation is m power 4 minus 1 equal to 0. It can be factored into m square minus 1 into m square plus 1. That is a square minus b square can be written as a minus b into a plus b. We are using the formula here. So next solve that m square minus 1 as m minus 1 into m plus 1. Again the same formula into m square plus 1. So this factor will be m minus 1 into m plus 1 into m square plus 1 equal to 0. So the solutions will be 1 minus 1 plus or minus I. So according to fundamental theorem of algebra, this equation should have 4 roots. So 1 minus 1 I minus I. Complex roots always we should consider as pair of conjugates. So the first 2 roots are real roots and the next 2 roots are complex roots. And first 2 roots are real and unequal. So the complementary function will be like this. CF is equal to C1 into e power x plus C2 into e power minus x plus C3 into cos x plus C4 into sin x, where C1, C2, C3 and C4 are arbitrary constants. So in this module, I represented the solutions of homogeneous type higher order differential equations, that is complementary function. How to find complementary function like that. In next module, I am going to present you about the solution of non-homogeneous type higher order differential equations with constant coefficients, that is mainly about particular integral. Thank you.